Where did you come from, Cotton Eye Joe? But I remember Cotton Eye Joe. I've been married a long time ago. Where did you come from? Where did you...
Well, welcome back this evening, coming at you live here from the Hills household. And our topic today is, we'll just title it here, Velocity Graphs Day 2. So we covered a video on velocity that was hopefully pretty familiar to you last night, and we're going to hit one more question tonight. So this question is going to have parts maybe A through G. And the beginning questions hopefully you feel real confident in, and they're not too bad. And then G is where we're going to focus a lot of our time. So let's go ahead and set up this scenario here. Squirrel starts at building A at time t equals 0, and then travels along a straight horizontal wire connected to building B. Perhaps that's something you can even picture. You've got a building here, we'll just call it building A, there's a wire attached to it, and here's building B. And basically, this squirrel is just kind of walking back and forth along this wire. The squirrel's velocity in feet per second is modeled by the piecewise linear function shown in the graph above. So I just want to be very clear and make sure we label this velocity. Okay, they're telling you that's velocity, and again, it's measured in feet per second, and let's pay attention to those units. Part A. After leaving building A, the squirrel realizes it left its acorn back at building A. What time does the squirrel turn around and head back to building A? All right, so again, remember, velocity covers your direction. Direction meaning left or right or up and down, and since they said it's horizontal here, we're talking left and right. So I just want to be clear that this section represents you moving to the right, this section would be the left, and the rest of this would all be the right since it's all above the x-axis. So hopefully just some common sense tells you, starting at 0, I'm walking to the right, and then I stop, I come to rest, remember that's when your velocity equals 0, and then this section you turn around and you walk to the left. So hopefully that's a pretty straightforward question. I would say the squirrel turned around at time t equals 4 seconds. All right, moving on. Part B. Part B says, at what time does the squirrel arrive back at building A? Give a reason for your answer. So remember, here's the squirrel leaving at time t equals 0. He starts walking along this wire, comes to rest, realizes he forgot his nut, or acorn, turns around, walks backwards, and comes to rest again. So this is implying that when he gets to t equals 7, he has arrived back at building A. And hopefully our reason for that answer was, I'm just going to kind of say it, you can put it into your own words here. From 0 to 4, the squirrel walked to the right. From 4 to 7, and came to rest there. From 4 to 7, he walked back to the left and came to rest again. Now you'll notice right here for one whole second, from 7 to 8, the squirrel is not moving. He's not moving to the left or to the right. So I just want to point out here that at this point, the squirrel is stationary. Okay, this squirrel is not moving for one whole second. Moving on, question C. Find the total distance the squirrel travels during the time interval, and I think I left the units off there. Let's add that in, 0 to 20. All right, so key trigger words, hopefully that are going through your head there, are total distance. There is a special formula for total distance traveled. And hopefully you're writing it down already. You'll recall that's the integral of the absolute value of velocity. And I'm going to throw the bound 0 to 20 on. All right, so total distance traveled. Make special note of where the absolute value is. It's not outside the integral. It's strictly around velocity. All right, so basically I just need to calculate all the areas from 0 to 20 of this velocity function. So go ahead and take some time and figure out how big each area is, and I'll do the same. Go ahead and pause me. I think that's 6 here. I'm going to go with -6. And hopefully that makes sense. He walked to the right and then walked back to where he came from. So those should be the same distances. I don't like this shape. I'm going to break it up. I'm going to go triangle, maybe a rectangle. I might even go further and break up into a bunch of shapes here. That's 3 by 4. That's 6 again, I believe. I'm going to go with 12. Whoops. I'm going to put a 2. 3 by 2 is 6. Half of that's 3. It looks like 4 and 2. All right, so my total distance traveled, just recall, I'm taking everybody's absolute value. So I'm going to start with 6, and I'm actually going to add to it this section. Again, I want its absolute value, so I'm going to add a positive 6, plus another 6, plus 12, plus, I'm going to squeeze these in, 3 plus 2, plus 2 plus 4. So I'm taking everybody's absolute value and making them positive. And hopefully you can double check my math there. I think that's 41. All right, I would consider those A through C so far pretty basic questions that hopefully everybody in the nation can get right. The next question here, part D, at what time is the squirrel the farthest from building A? I want you to stress that word farthest in your notes. Underline it, star it, do what you have to do there. If you are the farthest, that's implying that nobody can be farther than you. Therefore, you have to treat that like an absolute. Okay, if you're the farthest, nobody can be farther than you. Therefore, you're an absolute max or min. So at what time is the squirrel the farthest from building A, and how far from the building A is the squirrel at that time? So since it's absolute, again, we're going to treat it like the table. And I'm thinking in my head, set the derivative equal to 0. Okay, so in this case, I'm setting the velocity equal to 0. And I'm going to make my chart. Now I'm going to look up here real quickly. When does velocity equal 0? Well, it's 0, 4, 7, 8, and then not again. I got to use my endpoint of 20. So that's what we should have on our table here. So I'm going to have to scroll down and fix my table. We said 0, 4, 7, 8, and 20. Now I want to find how far this guy is, or I want to find basically its position. All right, so just use some common sense when labeling the table there. All right, so if I want to find my position at 0, basically I would integrate velocity from 0 to 0, which of course would be 0 area. If I want to find my position at 4, to get position I would integrate velocity from 0 to 4, because they told us time starts at 0. So I'll just scroll back up, and the area from 0 to 4 we said was 6. I would do the same from 0 to 7 of velocity. So I'll scroll back up. If I look from 0 to 7, those areas should cancel each other out. So hopefully we're going with 0. 0 to 8. Whoops, and I missed all my little DTs here. It's a little sloppy. Lastly, here's 0 to 8. You'll notice these canceled, so that gave me my 0, and then I'm still not accumulating any area here, so I still have an area of 0. And finally, 0 to 20. Now be careful, you are not taking absolute value in this case. All right, we are not taking absolute value. So I'm going to go back up here. That's implying that this 6 and this 6 are going to cancel each other out. So I basically need to add the 6, 12, 3, 2, 4, and 2. And if I did that right, I think that gets me an area of 29. So the question said, at what time is the squirrel farthest from the building? So I would say at t equals 20. And how far from the building is he? 29, and I believe we were in meters. I'm sorry, feet. 29 feet from the building. And I just want to take 2 seconds and just talk through that, make sure that makes sense to you. Here you're walking to the right, and then you walk back to the left. So these, again, should cancel each other out. And now from that point forward, all you did was walk to the right. So it should make sense that at 20, you are the farthest from the building. Okay, just a few more to go. Question E here. At t equals 3 and t equals 11, find the acceleration of the squirrel or explain why it does not exist. All right, so just keep in mind, you are staring at velocity. So if you want acceleration, you are now looking at the, hopefully you've said the word by now, slope. This is all about slope. So if I go to 3 and I want the slope here, basically anybody who's on that line is going to have the same slope. So I just need to calculate the slope of this line. And don't do anything more than, counting rise over run. I would say it's definitely a negative slope. I'm going to go down 3 and over 2. So I would say negative 3 halves at t equals 3. And then I need the slope at 11. So again, I'm going to go here. I'm going to get my slope. Hopefully you've already said to yourself that slope does not exist. Now just recall, I think we talked about it the previous day, we cannot say because it comes to a cusp or corner. That's not acceptable. Remember, you need to describe that with a limit definition. So the limit as t approaches 11 from the left of, I'm going to say v of t, does not equal the limit as t approaches 11 from the right of v of t. And actually, I don't think that's perfectly said correctly. Because I'm talking about slope, I don't actually want to say velocity. I want to say v prime of t for both of these. Because I'm not comparing their velocities, I'm comparing their slopes. So the slope on the left is not equal to the slope on the right. Okay, so let's just be real careful that we have the v primes in there. All right, we'll keep chugging here. Letter F, we're almost there. At t equals 4.5, is the squirrel speeding up, slowing down, or neither? Justify your answer. Well, again, hopefully the trigger there for speeding up and slowing down is telling you in your head you need to compare velocity of 4.5 to the acceleration of 4.5. So take a look at that graph one last time. Hopefully it is pretty straightforward. Find your 4.5, which is about here, and compare the velocity and the acceleration. Now again, I don't need actual numbers, I just need signs. I would definitely say the velocity has a negative value, it's below the x-axis. And now if I look at the acceleration or the slope here is also negative. So all I'm going to do is say v of 4.5 is less than 0, a of 4.5 is less than 0. Therefore, the squirrel is speeding up because v of t and a of t have the same sign. All right, well, we've made it to our last question of the night, so please take your time with this one. This is probably our most important one today, and I'm hoping this other stuff was review. If not, that's okay too. Just keep chugging. All right, letter G has 3 parts to it, and this has been on our exam at least twice in the past 3 years, so they're tending to like this question quite a bit. It says write expressions, so let's just underline that word, which is expressions, for the squirrel's acceleration, velocity, and position from building A that are valid for the time interval 11 to 16. So you're only looking at a piece of this graph, so I'm just going to kind of zoom in on it. I'm only looking from 11 here to 16 here. All right, so my goal is to write 3 expressions. So let's start with acceleration. Basically, I need to look at the what here. Remember, this is velocity, so I'm looking at the slope. And if you look at the slopes, I would say there's only 2 different slopes in this section that I've got narrowed down to in the green here. I would say this one has a slope that's consistent, and this has a consistent slope. So I'm actually going to write it in piecewise notation. I'm going to say this first piece has a slope of 0 from 11 is less than t is less than 14. Okay, so I'm describing when it has a slope of 0. And then second, I'm going to describe the slope here. And again, I'm just going to count my rise over run. I'm going to start at this point and end at this point. Definitely is negative. Negative 3 over 2. So I'm going to say I'm going to be a slope of negative 3 halves between 14 and 16. All right, so hopefully not too bad. I think that one's, probably the easiest of the 3. You're just looking at the slope and jotting them down. And notice my expressions talk about when these t values are true. All right, let's go get velocity. This time, to get velocity, it's actually pretty nice as well. I happen to be staring at a graph of velocity. So you're not writing the equation for the slope. You're writing the equation for exactly what you see. You have velocity, and you want to write the equation for velocity. So basically, when I look at this section, this is just the line y equals 4. So I would say my velocity is 4 from 11 to 14. That was the easy one. And now I'm just going to write the equation for this velocity. I need the equation of this line. So I'm going to take 2 seconds and do it off to the side here. I'm just going to use the point slope formula. Y minus y1 equals m times x minus x1. And I'm going to pick any point on the line. And this point, I mean, I would not pick anything in here. I can't really tell what those points are. So I'm just going to pick like an end point here. That point is on this line. So I'm going to say that's y minus 4 equals the slope, which we said was negative 3/2, times x minus 14. And I'm going to keep cleaning that up, so I've got y minus 4 equals negative 3/2 x. If I distribute that, I get negative 7, positive 21, I believe. And then I'm going to add over the 4. So that's negative 3/2 x plus 25. So I would put that in my equation here, negative 3/2 x plus 25. Oops, plus 25. And that's from 14 to 16. All right. The ugly one is last, and that's getting our position. Okay, so now to get the position, I'm given velocity. I clearly have to integrate to get position. The key is, you're doing this for any time in the interval, 11 to 16. Okay, so I can't just say I want the position at 12, or 12.5, or 12.25. I need to write this equation so for it's any time t. So I'm going to start off by saying I need to integrate starting at 11, and I'm going to go until any time t. Okay, now I'm going to have to do this in 2 pieces, and let me again show you why. Anybody in this section is going to have the same, I would be integrating under this line 4. Okay, anybody in this section, I'd be integrating under this line. Okay, so I do have to split these up. So let's start by getting this area for the orange section that I have here. I would integrate from 11 to any time t, so 11 to t, and that's the area under 4. So I'm going to throw 4 in as my integrand. Now, what I have to consider when I'm talking about my position is I have to consider how much area I already have. So remember, this area and this area cancel each other out, but you already have 6 to begin with. So I'm going to say that my position is the area from 11 to t of 4 dt, plus the 6 I already began with. That's my initial condition. And that will get me the position at any time t that I need. And I do want to make a note that my t values are going to be between 11 and 14. Okay. Now, I'm also going to say I could use the integral 14 to t of, and this time notice I'm going to find the area under this curve here, or this line, which we said was negative 3x plus 25. So I'm going to integrate negative 3, well, t I'll say, plus 25 dt, and add the 6 onto that. And this section will be good between 14 and 16. So take your time and review this piece if you have to. This is probably, like I said, the most important piece. And again, I had to do 2 separate pieces because the area was different under this section than it was in this section. Okay, and again, this piece is just adding on the initial condition of 6. So take good notes, and we look forward to seeing you tomorrow. Have a great night.